Welcome all of you. In the last class, we started discussing about nuclear overhauser effect. This is another interesting phenomena where you can get the correlation between two nuclear spins which are close in space. The requirement is only spatial proximity and not any J coupling. There is no need of a covalent bond between two spins. And I discussed about various factors that affect NOE, molecular motion, and then Larmor frequency, pathways available for their relaxation, and varieties of things we discussed, and also internuclear distance, everything. That is the dominant factor. And of course, we introduced about dipolar relaxation and allowed possible transitions. And I said if I take two coupled spins, there are single quantum, double quantum, zero quantum transitions. Zero quantum and double quantum are forbidden transitions in NMR, not detectable. Whereas single quantum are allowed as per NMR. But as far as the relaxation is concerned, these double quantum and zero quantum are allowed as far as relaxation is concerned, but not for detection. That's why I said NOE does not involve coherence. It involves only polarization, population difference. That's what we said. And of course, I extended further. I wanted to show what is a dipolar relaxation. I showed you when they are taking an example of two spins. The spins, both the orientation spins with respect to magnetic field remain same, but they can undergo tumbling in such a way one spin creates a local field, dipolar field at this side of the other. And it is an oscillating dipolar field. Of course, converse is to other spin also creates and other one. This is a dipolar relaxation phenomena. When the local field created at that time will allow the spins to undergo flipping. This is a dipolar relaxation. We discussed about dipolar relaxation, etc. And continuing further today, we will discuss further about how do we get positive NOE, how do you get negative NOE, what are the relaxation pathways allowed, all those things we will discuss. Of course, as positive and negative NOE depends upon what is called a relaxation pathway. How the nuclear spins are undergoing relaxation. To understand that, let us take two uncoupled homonuclear spins A and X. Remember, uncoupled I have highlighted with capitals because that is the important concept. There is no need of a J coupling. And I have taken a two spin system A and X, and I expect them to have a dipolar interaction in a magnetic field. That's all the condition, uncoupled homonuclear spins and having a dipolar interaction. As soon as you take the sample, put it in a magnetic field, what is going to happen? This is what is called a relaxation. Outside the magnetic field, the spins are all degenerate. They are randomly oriented. There is no separation of energy states. We all know. As soon as you put the sample in a magnetic field, within a short time, within that that is called a longitudinal relaxation time. I didn't discuss about longitudinal transverse relaxation times T1 and T2 in this course because that was discussed in the previous course. That was not the main aim of this course. And there are different relaxation like T1 and T2. The spins, because if the time within the longitudinal relaxation time, they start getting equally distributed among the energy levels within a short time, less than are comparable to relaxation time, the spin get redistributed like this. I have taken the example of two spins, 4 energy states, beta beta, alpha beta, beta alpha and alpha alpha. Already we discussed this is A transition, this is A transition, X transition, X transitions. Each of these two transitions have numbered A1, A2, X1, X2. And I told you already, since there is no J coupling, frequencies are identical. A will give 2 transitions, B will give 2 transitions. I have, for the sake of understanding the intensity of the peaks, just to identify, to get the intensity of the peaks, I have written certain populations here. Some of the spins here I have written some number. Why did I write that number? Because I just wanted to ensure that the population difference gives me the intensity, and in a weakly coupled or two spin system which are not even coupled, there are only 4 possible transitions, 2 of them are equal. For each spin, 2 of the transitions are equal. So I want to ensure that the transitions should have identical intensities. That's why I have written these are the possible distribution immediately after putting the sample in the field, magnetic field. Immediately after putting. I am not even waiting for the T1 period. If I wait for the T1 period, there is a redistribution here. It is as good as, this is what happens if you understand NMR. You put the sample immediately, let us say your sample has a very long relaxation time. You start collecting the signal, you will not get it because you have to wait for the spins to align and the sense population redistribution should take place. Now I am not allowing the population redistribution to take place. Immediately after putting the sample, I look at the population distribution, it is like this. Now take the population difference and find out the intensity of the peaks. A2 transition 2 minus 2 0, 2 minus 2 0, 0 0. All the 4 transitions 2A and 2X which are equivalent have 0 intensity. This is exactly what happens. As soon as I put the sample in a magnetic field, if you don't allow the spins to completely attain thermal equilibrium, then you will not get any signal. This is what happens. No signal for A or X. Now what we will do is, we will wait for some time. That time is the relaxation time. That time is called T1. T1 is a time it's called longitudinal relaxation time. Is the time required for the spins to attain thermal equilibrium. That is the growth of magnetization along the z-axis. Population gets redistributed with time because of the relaxation forces. You see the difference. Immediately after putting the sample is one phenomena. Now I have waited for some time. Let us see what is the population difference. See, there is some redistribution has taken place. Now there are 4 spins here, 2 here, 2 here and no spins. But never be under the impression there are no spins in the state here beta beta. Okay, there are spins there, but for the sake of understanding the intensity of the peaks, I have taken some number. That does not mean there are no spins in the higher energy state beta beta state. There are spins. So for calculation, this is 4, this is 2, 2 and 0 is taken. I have after waiting for sufficiently long time, that is T1 period. Now let us calculate the intensity of both the peaks for A and X. A2 transition 2 minus 0, intensity is 2. Here A2 transition 4 minus 2, 2. X 2 minus 0, 2. X1 2 minus 4 minus 0 or 4 minus 2 is 2. Exactly now each X transitions, 2 transitions of X, 2 transitions of A, both of them are equal intensity. That is why we get 2 singlets. 2 peaks are same frequency overlap and both of them have equal intensity, which is 2 2. Okay. X transition intensity is true, Y is 2 after thermal equilibrium. After the time T1 when you put the sample in a magnetic field. Let us see now. After some time we know that A and X transition have equal intensities, and I told you spins in the beta beta state are there. Only for calculation purpose it is taken as 0. Never be under the impression there are no spins in the beta beta states. What we will do is, continuing further, I will saturate transitions A1 and A2. I will equalize the population. What do you mean by saturation? Making the population bit of both the states equal. I will saturate transition A1 and A2. What I will do? This was the equilibrium population, right? 4220. When I equate equilibrium, when I make sure that it is saturated, now these two become equal, these two become equal. This is what happens. I have saturated both A transitions. I am not touching X transition at all. X spin is remaining same. But we will calculate the intensity now. A transition has 0 intensity obviously because spins are saturated, no signal will be there. Both are 3 minus 3, 1 minus 1 0, so no signal for A. What about X? Calculate the X intensity. 3 minus 1 2, 3 minus 1 2. So after some time, what it means here is you have saturated and of one of the spins and still got 2 2 intensity. It means saturation will not alone give you any enhancement to the intensity. Let us wait for some time after saturating. what is going to happen? You will not be continuously saturating. You are saturating for some time and then take out the RF. The system has to attain equilibrium. It will come back to thermal equilibrium. That means the saturated spin, when it attains thermal equilibrium, there is a population redistribution, and you can again calculate the intensity now. It is going to be, when it comes back, you have equal intensity again. You have 2, 2, 2, 2. What is the situation what happened now? In the sense, we saturated one of the spins, both the transitions. We saw change in the intensity is 2. After some time, allow the spins to come back to thermal equilibrium. Still it is 2 only. There is no change in the enhancement. There is no change in the intensity of the signal at all. That means there is no over or enhancement. What does it imply for you? Saturation alone does not cause any change in the intensity or will not give rise to over or enhancement. Then why do you get, what do we have to do to get the NOE? Let us do one more trick now. We will saturate, at the same time we will introduce what is called cross-relaxation. What is cross-relaxation? The relaxation that occurs between two spins via dipole-dipole interaction. When we discuss about relaxation, I have discussed this at such a lot of thing about in one of the previous courses. The relaxation that occurs between two spins via dipole-dipole interaction we will introduce now, cross-relaxation between two spins. Now in this presence of irradiation of A spin, the transition probabilities have varieties of effects. Okay, one, WA transition, the single quantum, then there is no effect since the A transition is being irradiated. W1S has no effect since the S transition is already saturated at equilibrium. In the presence of irradiation of A spin, transition probability have different effects. When I irradiate A spin, transition is being irradiated, there is no effect, but S spin, no effect since S spin transition is already at equilibrium. That is okay. Something interesting. We will allow the system to relax in the presence of irradiating field using different pathways. What are the different pathways? The nuclear spins, here we saw, when we are attain thermal equilibrium, it will start coming back like this. From one, this is called single quantum transition, single quantum pathway. Spins are relaxing through single quantum pathway. That is what I said here. Single quantum pathway only we are seeing. There is no effect. But what we will do is, we will allow the spins to relax through different pathways. That is, double quantum pathway between alpha alpha and beta beta spins, or zero quantum pathway between beta alpha and alpha beta states. Why not? The spins undergo transition between these states. This is a double quantum relaxation, this is zero quantum relaxation pathway. What will happen now? If you allow the spins to happen like that. In the previous example, previous slide, the spins were relaxing through single quantum pathway only to attain thermal equilibrium. But we will attain thermal equilibrium with a different pathway. What we will do is, now let us say we have saturated A spin, both the A spins are saturated. This is situation. I have saturated, population difference is 0. We will allow the spins to come through, not through single quantum, but directly through double quantum pathway like this. What happens? I have not allowed the spins to come through single quantum. Then it would have been a different thing. So this would have come here, this would have come here, and we would have attained thermal equilibrium. That is a single quantum relaxation pathway. But I have chosen double quantum relaxation pathway. Now let us calculate the intensities of both A and X spins. Now A transition, 1 minus 0 is 1, 4 minus 3 is 1. A transition has 1 intensity. Okay, 1 intensity. See the X transition now. X transition is 4 minus 1, 3. 3 minus 0 is 3. A transition is 1, whereas X transition is 3. This is what happens. When I calculated, allow the spins to come through double quantum relaxation pathway. If I recalculate the intensities of A and X spin, A intensity is 1, X is 3. There is a 50% gain in the intensity for one of the peaks. Okay, what happened here? We saturated 8 spin. That's what should happen. If I saturate one spin, the change in the intensity of the non-irradiated spin is what is NOE, I told you in the previous class, the definition of NOE. I am irradiating A spin, there must be change in the intensity of the X spin, and that's what happens here. I irradiated A spin, a X spin has increased the intensity by 50%. There is a gain in the intensity. This is a situation called positive NOE case. If the spins undergo relaxation through double quantum pathway, there is a positive enhancement of the signal intensity by nearly 50%, and you are going to get positive NOE. Okay. Anyway, this is not the important thing, we are not discussing. This is a case of positive NOE. Let us go to the other one. I continue to irradiate at the low power, wait for the spins to attain equilibrium. It will happen. It will all come back to original state where we started with 4220. Here again both the A and X spins have equal intensity transitions 2, fine. So what we did here, we irradiated A spin and allowed it to come through double quantum pathway. We saw gain in the intensity for the X spin. Continue low power irradiation, allow the system to attain thermal equilibrium, then this is the spin population redistribution. Okay, that's fine. I will consider another situation. Again I have saturated A spin, both I have made equal. But I will do one more thing now. Instead of allowing the spins to relax through double quantum pathway, why can't I allow it to relax through zero quantum pathway like this? If the spins are allowed to relax through zero quantum pathway, there is a different phenomena now. Let us now calculate the intensity. Intensity of A spin and X spin. X spin intensity is 2 minus 1 and 3 minus 2, both are intensity 1, 1. So earlier case X was 2, now it became 1. Of course this is the irradiated spin, you will not worry. What happened to X spin? I irradiated A spin, allowed the spin to relax through zero quantum pathway, the intensity came down by 50%. There is a loss in the intensity. When the spins relax through double quantum pathway, there is a 50% gain in the intensity. This is the difference. Okay. This is a case of negative NOE. Now you understand what is the relaxation pathway which is responsible for both positive and negative NOE. A double quantum pathway is if it is a dominant relaxation pathway in a spin system, you have a positive NOE. If the relaxation is a zero quantum pathway that is dominant, then you will have negative NOE. So the dipolar relaxation is one of the root causes for NOE, and the pathway that is available for relaxation defines whether the intensity is positive or negative, or whether it is a positive NOE or negative NOE. Continue low power decoupling, again attain thermal equilibrium. That's all what happened. Here come back to equilibrium. So this is the situation what we do. In an NOE, you irradiate one of the peaks and see the effect on the other spin. What happens within the system you don't know. Spins can relax through zero quantum, double quantum or other way. There is also single quantum relaxation is also possible. We saw in the first one, and where there was no effect on the intensity at any you after irradiating and allowing it to come to equilibrium, the intensity remains same. So double quantum and zero quantum are the only important phenomena. But W1 single quantum relaxation pathway do not create NOE. In a molecule or any spin system of your interest, if this relaxation pathway is a dominant phenomenon, that is a dominant relaxation pathway, then you will never see NOE. So in any given molecule or any given spin system of your interest, if you want to see NOE, the spins must relax through double quantum pathway or through zero quantum pathway. That is an important condition. Okay. When will it happen? When is W2 dominant? When is W0 dominant? If W2 is the efficient pathway for relaxation, it can happen in the case of small molecules where there is a fast motion and the frequency of tumbling is larger. Large frequency is there. So, this W2 relaxation pathway is dominant for small molecules which is undergoing fast motion. That is where you get positive NOE. All right, that yields positive NOE. So, small molecules generally, of course, depends upon various phenomena like alarm frequency, etc. You will have a W2 relaxation pathway and give positive NOE. What happens if W0 is the efficient pathway? This is only for the large molecules like big proteins, etc. These molecules cannot tumble very fast like small molecules. They are little sluggish. As a consequence, they undergo slow motion and small frequency will be generated. As a consequence, you will get negative NOE. Say W0 is, if it is dominant, you get negative NOE. It can happen only for big molecules, large molecules. Small molecules, W2 is generally dominant and you get positive NOE. So, please remember, these are the important sources of relaxation pathway, that is for a positive and negative NOE. But in reality, in a given molecule, you do not know what is happening inside the nucleus. They are not, when we for the purpose of calculation, I took it individually. What happens like that? But in reality, they are not separate, they are not exclusive processes. Both the phenomena are simultaneously happening. One may be dominant, other may be less dominant, or both may not be dominant, both may not be existing. We do not know, both may be dominant, we do not know. So, there is a forces which is going on. There can be a competition between both the processes. Not only between these two, there can be competition along with single quantum transition also. That is relaxation pathway. So, all the three W1, W2, W0 are not exclusive processes. There can be competition among them. They are competitive processes. So, that means, please remember this statement. Positive and negative NOE is dictated by the dominant relaxation pathway, which is the relaxation pathway. So, if you know this is the dominant 0, this is positive, this is dominant negative NOE. That is all you have to understand. All right. In summary, please remember, when W2 is, or we are comparing only W2 and W0. W2 when it is very, very dominant, large, compared to W0, NOE is positive. When W0 is large, that is dominant, NOE is negative. When W2 equal to W0, there is no NOE. You will not get NOE at all. That dominant is W1. Okay. We can even calculate NOE. There is a way we can calculate NOE also. How do you calculate? What is NOE, etc. There is a process for this. How do we get the NOE? Percentage of NOE we have to calculate. I irradiate A and get the S spin. Generally, usually we always say I and S spin. This phenomena, the terminology came because when the NOE was discovered, first it was electron, electron that was irradiated and see the enhancement in the signal intensity. But here we are doing only with nuclear spin, but still term I and S remains same, does not matter. The gain in the signal intensity due to NOE is given by a famous equation called Solomon equations. It is a qualitative statement for the phenomena of steady state NOE. It is a very big description is there, and this is itself takes enormous amount of time to discuss, to arrive at the equations, everything. There are two books on NOE itself by Nagel and Mike Williamson. Two books exclusively on NOE itself. Imagine the vastness of this topic. So, there is this discussion itself. I do not want to go to mathematical description to arrive at everything, but this is the final expression called Solomon equation. What this will do is this one. If eta is always referred to as a symbol for gain in the NOE factor. Bracket S means I am irradiating that spin. I am irradiating the S spin and I want to see the gain in the intensity for I spin. What happens? If I irradiate S, see the gain in I spin. That is given by this expression. W2 and W0 we already said the relaxation pathways. W1 that is the transition probabilities, relaxation probabilities. And this in short form is written like this. W gamma s and gamma I into this range, this one. This is called cross relaxation. This is, I will tell you this thing. This is an NOE term first of all. We will say this is an NOE term. And this, whatever the entire term given in the bracket is a NOE term. And W2 minus W0 is called the cross relaxation rate constant. This is difference in double and zero quantum transition probability. The transition probability W2 and W0, if we find out the difference, that is called cross relaxation rate constant. The bottom denominator what we saw is the sum of all the three terms. This is the longitudinal dipole relaxation rate constant. Rho, this is sigma. These are the two factors which contributes to NOE. This is the denominator, this cross relaxation term is in the numerator. This is summarized and put like this as a factor like this, gamma s over gamma I into sigma s over rho is. This is the factor. Why we introduce gamma? What was the need to introduce gamma? Remember, if it is a homonuclear spin, we don't need to worry. Gamma is identical. But we can also do NOE between heteronuclear spins. We can get NOE between heteronuclear spins. That is the reason, in which case the populations are different. For example, carbon 13 is 4 times less populated, difference in population is 4 times less than that of protons in a given magnetic field. So gamma factor has to be taken into account to take into account the equilibrium population of different nuclear spins, heteronuclear spins. That's why gamma is taken into account. When I said when I take protons, we don't need to worry about it. So all we have to deal with is sigma is over rho is. That's all important thing. Cross relaxation over the longitudinal relaxation rate constant. So W2 minus W0 define what is the sign of NOE. That's the important thing. What are these the rates of W2, W1, W0 processes? If somebody can answer the question, if somebody asks the question, what is W2? Okay, we transition probability. What are these rates? How fast they will undergo transition? What is the rate of W2, W1, W0? That depends upon another function called spectral density function given by J of omega. It depends upon spectral density functions. And what is that for the case of W1? This spectral density function, if you look at JW, it is identical to Larmor frequency of the spin that is undergoing flipping. That is, what is our Larmor frequency? Whatever let us say I am recording the spectrum in 400 megahertz spectrometer, W1 is 400 megahertz. That's all. If both the spins are the same homonuclear spin, Larmor frequency around 400 only, both of them 400. That is the W1 transition probability. The frequency of W1 is nothing but the Larmor frequency. What is W0? W0 is the energy difference identical to difference between Wi minus Ws. What is Wi and Ws? Resonating frequency of two heteronuclear spins is what? Homonuclear spins. If I take homonuclear spins, I am dealing homonuclear spin now. When W and Ws same, let us say proton, they are two different chemical shifts. Resonating frequency is just difference in the chemical shifts. What is that chemical shift value? It is of the order of few hertz or few kilohertz. Remember, W1 is megahertz, W0 is few kilohertz or few hertz. What is W2 then? W2 is the sum of the resonating frequencies of Wi and Ws. What is the resonating frequency of two spins? Both are in megahertz. This is 400 megahertz, this is 400 megahertz, let us say. Then what is W2? W2 becomes 800 megahertz. That is the difference. So W0, W1, W2 depend upon spectral density function, which in turn depends upon various factors. One is W0 depends upon Larmor frequency, W1 is Larmor frequency, W0 is the difference in the chemical shift, difference between the Larmor frequencies, and W2 is the sum of the Larmor frequency. So these are the three factors. W1 is Larmor frequency, W0 is difference in the Larmor frequency, and W2 is sum of the Larmor frequency. These are the three factors which you have to consider. All right. Let us say what is the spectral density function in numbers. for proton at 400 megahertz, just to give you the numbers. Of course, W1 is 400 megahertz, W2 is double of that, sum of the alarmer frequency is 800 megahertz, W0 is a difference in the chemical sheet few kilohertz. That is all the spectral density functions. The frequencies are of this order. Only 3 we have to consider. I am considering 2 homonuclear spin systems. Then what is the spectral density? You may ask me a question. Okay, we said spectral density function everything. What is the spectral density means? Of course, it is a distribution of the frequencies of oscillating dipolar interaction. I told you about dipolar interaction, 2 spins. Both of them oriented in the same direct orientation with respect to magnetic field. That orientation won't change. But then when they undergo a tumbling motion, the local field at the side of the other nuclear spin start changing. That is what we saw. One nuclear spin induces dipolar field at the side of the other nuclear spin. That keeps changing. And that is what are the frequencies which are going to get? The distribution of the frequencies of the dipolar field, oscillating dipolar field, that is created at the side of the other nuclear spin because of the tumbling motion is nothing but JW. It is called the spectral density function. So, it is nothing but the distribution of frequencies of the oscillating dipolar interaction term. Okay. Now, to induce spin transitions, molecules must tumble at the appropriate frequency to provide the fluctuating field. Remember, this is a very important point. Let us say there is a transition has to undergo between 2 energy states. This has some energy. Of course, when we discuss about the relaxation everything in one of the previous courses, extensively I discussed this. To induce the spin transition, the molecule must tumble at appropriate frequency. Then only the spins will undergo transition. Then what is the tumbling frequency? It should match with this. When the tumbling frequency matches with this energy separation, then spins will undergo transitions. So, this is the important thing. Dipolar fluctuating field should match with this energy separation. And next question is, where do you get this fluctuating field? Of course, a lot of factors are interconnected. First, spectral density function, that is has some frequency which is related to alarmer frequency. And where does the spectral density function come? It is because of the fluctuating difold magnetic field created because of the tumbling motion of the nuclear spins. But what is the reason for fluctuating magnetic field? Where do you get fluctuating field, electromagnetic fields to generate this dipolar field at the set of other nucleus? That is because origin of the fluctuating magnetic field in solution state, it is the motion, rotational motion of the molecule. Molecules are not staying steady. They are not the spins aligned with the magnetic field, but this in turn generates magnetic field because they are undergoing fluctuation. That is what we saw in the figure. When the 2 dipoles, I took the example, one dipole is stationary, let us say I took the example for stationary just for calculation purpose, and the other one undergoing tumbling motion while creating magnetic field all through that other spin, keeping both the orientation with respect to magnetic field same. So, spins stay aligned with the external magnetic field, but in turn while undergoing motion, tumbling motion, generate fluctuating magnetic fields. That is the fluctuating magnet at the frequency of the rotation molecule when they are undergoing rotation. So, this is the origin of the fluctuating field, and this is given by this thing. Molecules can undergo tumbling, fluctuation, rotation, fluctuation. These are all the important factors. So, if molecules were steady, let us say you take a perfectly rigid solid, no motion at all, neither translational or rotational motion, in which case spins take enormous amount of time to relax, it may not relax, it may take ages to relax. These fluctuating fields are dipoles that is generated because of at the site of one spin because of the motion of the other spin causes this type of, gives rise to this type of spectral density function which is responsible for relaxation. And these fluctuating fields are the pathways for the system to release energy, and that causes relaxation. You understood what causes relaxation? Spectral density function which has different frequencies. Where do this comes? Fluctuating density frequencies come for this fluctuating magnetic field. How do fluctuating magnetic field comes? It is because of the molecules undergoing motion, rotational motion, tumbling motion like that. And these tumbling motion frequencies matches with this fluctuating, this rotation frequency of the molecule, and that causes flipping of the spins. And this rotational correlation time is molecules when they undergo rotation. This tells us about the motion of the molecule. How fast the molecules are undergoing motion, how fast are they going, fast or slow, that is defined by tau c, called correlation time. I will discuss more about this since the time is getting up. I will discuss more about the correlation time, everything in the next class. But right now you understand, today we discussed a lot about NOE. In this class we discussed about various relaxation pathways available for spins to relax, and we discussed about the spectral density function. I said the spectral density function depends upon has different frequencies, and W1, W2, W0, the spectral density function for these things is nothing but W1 is Larmor frequency, W2 is the sum of the Larmor frequency of the two spins, W0 the difference of the Larmor frequency. In a given spectrometer frequency W1, let us say 500 megahertz is 500, for W2 is 1 gigahertz, whereas W0 is the difference of the chemical shifts. And these fluctuating fields comes because of the rotation of the molecule, which in terms generates the fluctuating field at the site of the other spin, which causes spins to undergo flipping, causes dipolar relaxation. And all these factors, if let us say in a given molecule, if the fluctuating field at the frequency generated is twice the Larmor frequency, then W2 is dominant. If it is half the Larmor frequency, W1 is dominant. If the frequency of the fluctuating field is difference of these chemical shifts, W0, then that is dominant. This is why this is how you have to understand what happens to dipolar relaxation, how they contribute for the NOE. Okay, with this I am going to stop today. We will continue with this relaxation time, correlation time, etc. in the next class. Thank you.